Okay, folks, it is that time of the morning, so I'm going to go ahead and get started. Just a quick note, it's above this, but the lab today will be in room 103. So down the hall and to the left. That way we can sit in chairs and stuff like that. And it will be similar to this, but at least I can see your faces in case there are questions. Any questions for me before I get started with the day today? Okay. So the last thing we were discussing on Tuesday was enthalpy. And enthalpy is represented by a capital H. It is a state function. It doesn't, in other words, enthalpy, it doesn't matter how you get from point A to point B. It just matters what point A and point B are. So in a chemical reaction, it doesn't matter if there's multiple reactions involved. All that matters is what are the reactants and what are the products. Now, enthalpy can be a positive value. If it is a positive value, that means that it is an unfavorable process with respect to enthalpy. Again, it's an unfavorable process with respect to enthalpy. And what that means is if you have a positive enthalpy, it means you're going to have to constantly be adding energy to the reaction in order to make the reaction progress. Now, if a reaction is a positive enthalpy, it means that the process is considered to be endothermic. And it means that if you list the enthalpy by itself, such as in this particular problem, you will list it with a positive sign on the enthalpy. That positive, again, remember, positive and negative for what we're doing does not mean the same thing as it does in the mathematical concept. It means, is the reaction, are we constantly adding energy to the reaction? Or are we giving energy off from the reaction? So if you list enthalpy by itself, you will list it with a positive value. Now, you can also show enthalpy within the reaction. And if you show enthalpy within the reaction, you would simply list the enthalpy. And it will still be a positive value, but it's going to be shown on the reactant side of the equation. So this is just an example of what we talked about on Thursday, with a couple of examples as to how it is displayed, how enthalpy is displayed associated with reactions. Any questions about those pieces of the puzzle? I'm trying to give folks time to write, but I see her writing. I'll scoot a little bit. Now, we can also have a negative enthalpy. When you have a negative enthalpy, that is considered to be a favorable process with respect to enthalpy. It is favorable, and what that truly means is once you get the reaction started, it's going to occur. You don't have to keep adding energy to make it happen. Once you get it started, the reaction will occur. Now, if you have a negative enthalpy, that means that the process is considered an exothermic reaction. Now, I will give you an idea of a couple of these things. It's always a challenge for students when they first see this concept to remember endothermic goes with reactants, exothermic goes with products. So I've, over the years, looked at these words carefully to try to come up with a way to help you memorize that. Endothermic begins with EN, just like the word enter begins with N. And what enters into a reaction? The reactants. Exothermic begins with an EX, just like the word exit begins with an EX. And what exits a reaction? Well, that would be the products. So if you have an exothermic reaction, then if you show the enthalpy all by its little lonesome, you're going to put a negative in front of it. But, and this is the big but, if you show the enthalpy as part of the reaction itself, it's simply shown as one of the products. Now, you're going, but this is negative. Why is that positive? Remember, energy is not negative. Energy is not positive. It tells you which direct, well, it's always positive, I should say. Energy is not negative, ever. That sign is telling you where it goes. If it's negative, it goes from the reaction to the surroundings. But energy is always a positive value. It just tells us the negative, and the fact that it's listed in the products is telling us the same thing, that energy is a product of this reaction. Questions about these concepts? Again, this is where we ended class on Tuesday, but I wanted to, on Tuesday, I went through it rather quickly. I gave you simple phrases, and I wanted to spell things out a little bit better so that as you're studying, you would hopefully understand these concepts a little bit better. Now, I do want you to notice one thing, which is leading into what we're going to be talking about in a minute. Let's see if I can pull it up enough. Okay, you will notice the reactions that I have going on here. These reactions are simply the reverse of one another. And looking at these reactions as the reverse of one another, you will notice that the value of the enthalpy is identical. The only difference is the sign. Photosynthesis, which is the top reaction, is not a favorable process. It requires sun to keep it going. It requires energy from outside sources to keep it going. But when we burn glucose, in the Krebs cycle, and the glycolysis chain to the Krebs cycle. When we burn glucose, it is a negative process. It is an exothermic process. So again, these two processes, the values are the same. They are just opposite in sign. So how do we determine the enthalpy of a reaction? You've actually already had some experience with this experimentally. Experimentally, you would use calorimetry, whether that is going to be a bomb calorimeter, which is at constant volume, or whether that is going to be a coffee cup calorimeter, which is at constant pressure. you use calorimetry to determine the enthalpy experimentally. And when we do so, to get the enthalpy of the reaction, we take the heat of the reaction, we divide it by the number of moles of that reaction. But, folks, I'm not going to go to the lab right off the bat and try something. Number one, I don't want to take a chance on something blowing up in my face. Number two, I don't want to sit there for a year trying to get something to happen. So I don't always start out with the experimental. I start out with the theoretical. And there are actually 3 ways to determine the theoretical, although we're only going to use 2 in this class. To determine the enthalpy theoretically, you can use bond dissociation energies, which is the one we will not be doing. You can use Hess's law, and you can use enthalpies of formation under standard conditions. These will allow you to determine the enthalpy experimentally. These will allow you to determine the enthalpy theoretically to determine whether you want to go to the lab and actually do the experiment. So the first thing we're going to be working with is going to be Hess's law. But before we can get into Hess's law, you got to understand enthalpy relationships. The first one I just spoke to you about with regard to photosynthesis compared to the glycolysis chain and so on and so forth. The first one I already spoke to you about, and that is, if you reverse a reaction, the sign on the enthalpy changes. Numerically, it's the same value, but the sign changes because it's no longer going to be a reactant, it would be a product. Or it's no longer going to be a product, it's going to be a reactant. So if you reverse a reaction, you're going to flip the sign of the enthalpy. Now, the second one I did not discuss, we have not discussed at this point. But this one we're going to come back to at not only with Hess's law, but we're actually going to come back to this probably briefly on the Thursday after exam 4. And that is, if you multiply a reaction by some variable, then you multiply the enthalpy by that same variable. So if I multiply the entire reaction by 2, then I would multiply the enthalpy by 2. Now, let me explain why number 2 works, or why we have to do number 2. Let's think about it. And I actually gave you an example on Tuesday. Tiny amount of water doesn't require much energy to go from liquid into steam. But a large vat of water requires a large amount of energy to go from a liquid into steam. So we have to multiply the enthalpy by the same variable because the quantity matters. And the last one really plays into Hess's law. And that is, if a reaction is the sum of 2 or more what I call subreactions, then the enthalpy of that reaction will also be the sum of those reactions, those subreactions. questions about the rules because we are fixing to get into some examples. I'm going to work an example of each rule first, and then we're going to apply the examples to Hess's law. Okay. So let's take this is one of my favorite reactions. I don't know if I've already said this to this class, but I tend to be a pyromaniac. I love reactions that involve fire. And this, folks, is the thermite reaction. The thermite reaction is a very useful reaction. It produces iron in the form of a molten iron or a liquid iron. And they use this particular reaction to repair railroad tracks or things like that, because you could just drop the stuff directly onto the brake. Instead of bringing the railroad track in to get it fixed, you just drop this stuff directly on the brake. So it's a very useful reaction. I like it because, like I said, I love fire. Now, if you take aluminum and you react aluminum with rust, which is iron 3 oxide, you will get out molten iron and you'll get out aluminum oxide. That reaction is extremely exothermic, producing 732.5 kilojoules per mole of energy. Now, if I were to take and reverse this reaction so that I took the iron in liquid form and reacted it with the aluminum oxide, to form aluminum plus iron plus rust, iron 3 oxide, then the enthalpy of this reaction would be a positive 732.5 kilojoules. So in other words, while the thermite reaction, once you get it started, it's going to go on it all on its own. The reverse of that reaction is going to require continuous heat to make it occur. That's what our signs mean. Yes. Okay, so the question was, is there a numerical value that determines how exothermic or endothermic something is? The answer to your question is there isn't a particular numerical value. Again, if it's negative, it's exothermic. If it's positive, it's endothermic. There isn't a particular numerical value that tells us anything. We have to do calculations. Okay, so let's look at the formation of ammonia. And that is a negative up there, negative 92.4. So when you take nitrogen gas and react it with hydrogen gas, you will get ammonia gas. And that reaction, once it is started, it's going to go all on its own. It gives off a negative 92.4 kilojoules per mole of energy. Now, if you take and double everything,
then you're going to take the enthalpy from the prior reaction and you're going to multiply that by 2 as well. So in other words, if you do that, then your delta H is equal to a negative 184.8 kilojoules per mole. If I were to take this reaction and instead of multiplying it by 2, I instead were to divide by 2. So that I have 1/2 N2 gas plus 3/2 H2 gas going to form NH3 gas. Then I would need to take that enthalpy and divide by 2 as well. So that means that the enthalpy of this last reaction is equal to a negative 47.1 kilojoules per mole. For our last process, if you'll recall, I said that if the reaction is the result of some subreactions, then the enthalpy is the sum of those subreactions. So looking at this, now let's figure out what the reaction is. To figure out what the reaction is, what you're looking at is, okay, I have C2H4 gas on the reactant side. Do I have C2H4 gas anywhere on the product side? If so, they would cancel, or up to the appropriate number. I have oxygen gas on the reactant side. Do I have oxygen gas on the product side of any of the reactions? If so, they would start to cancel. So that's what we're going to do to figure out what the reaction is we're going to go back and forth and look at everything to see if we can cancel some stuff out. So what I noticed is I have 3 oxygens and another 1/2 oxygen. That makes a total of 7 halves on the reactant side. And I have 7 halves oxygen on the product side. So that means that those oxygens are going to cancel out. Now, folks, you got to make sure you not only have the substance, but you got the correct state of matter. I have 3 oxygen gases plus a 1/2 oxygen gas on the reactant side. That it makes 7 halves oxygen gas on the reactant side. And I had 7 halves oxygen gas on the product side. So they canceled. I noticed that in this first reaction, I have 2 CO2 gas on the reactant side. In the second reaction, in the first reaction, I have 2 CO2 gas on the product side. In the second reaction, I have 2 CO2 gas on the reactant side. So those will cancel out. I noticed that I have 2 H2O liquid on the reactant side. I'm sorry, I keep saying reactant, I meant product. I have 2 H2O liquid from the first reaction on the product side. I have 2 H2O liquid from the third reaction on the product side, making a total of 3 H2O liquids. I also have 3 H2O liquids on the reactant side. So that is going to cancel out. Anything that did not cancel out comes down into the final equation. So C2H4 gas plus H2 gas produces ethane gas. Now for this last reaction where it's ethylene or ethene and hydrogen reacting to form ethane, I added the 3 subreactions together. So to get the enthalpy of the reaction, I'm going to add the 3 enthalpies together. And when I do so, I get a negative 136.8 kilojoules per mole. So again, the third thing I stated up above is that when your reaction is the result of the sum of 2 or more subreactions, then your enthalpy is the result of the sum of the enthalpies of those subreactions. Yes. Yeah, for this type of problem, yes, it would be given to you. And you would be asked to calculate the enthalpy but for this final reaction. Yes. So I said that these 3 things were going into Huss's law. We will also use some of these concepts for stoichiometry. But let's actually get into Huss's law. Huss's law basically says, regardless of the multiple steps of a reaction, in other words, regardless of the subreactions, the total enthalpy change is the sum of the enthalpies of those steps. Now, let's look at some examples. Calculate the enthalpy for the reaction 2 SO2 gas plus 2 phosphorus solids plus 5 Cl2 gas goes to make 2 SOCl2 liquid plus 2 POCl3 liquid. Given SOCl2 liquid plus H2O liquid goes to make SO2 gas plus 2 HCl gas. That has an enthalpy of 10.3 kilojoules per mole. PCl3 liquid plus 1/2 O2 gas goes to make POCl3 liquid, and that has an enthalpy of negative 325.7 kilojoules. P solid plus 3/2 Cl2 gas goes to make
PCl3 liquid with an enthalpy of negative 306.7 kilojoules, and 4 HCl gas plus O2 gas goes to make 2 Cl2 gas plus 2 H2O liquid with an enthalpy of negative 202.6 kilojoules. Okay, so when I work with a Hess's law problem, the first thing I do is I look at my very first substance, SO2 gas. And I look for an equation that involves SO2 gas. When you look for an equation that involves SO2 gas, the only one you're going to find is this first equation. None of the others have SO2 gas in them. Now, as I'm looking at the target equation, which is what I call this first one, I notice that the SO2 gas is a reactant. But in the equation I was given, it was a product. So to get the SO2 where I need it, I am going to have to flip this equation or reverse it. I also noticed that I want 2 SO2s, but I only have 1 SO2. I want 2 in the given and the desired equation, but I only have 1 in the given. So I'm also going to have to multiply that equation by 2. So this first equation becomes 2 SO2 gas plus 2 HCl gas goes to form 2 SOCl2 liquids plus 2 H2O liquid. Since I flipped the equation, I'm going to change the sign. And because I multiplied it by 2, I need to multiply the enthalpy by 2. So that enthalpy becomes a negative 20.6 kilojoules. Yes. You're right. Thank you. Questions about what I've done so far and why? The why is because I needed that target equation. The top equation is what I need, and I've got to make these other 4 equations match what I need. I always start with the first substance, and then I'm going to move to the next substance. And then so you're going to walk through that top equation until we've covered everything. Okay, so my next thing is I need phosphorus solid specifically. And looking through all of the equations, the only equation that has phosphorus in solid form is going to be the third equation. I need phosphorus as a reactant. That's fine because my phosphorus is a reactant. I need 2 phosphoruses though, and so, but I only have 1. So I'm going to have to multiply that third equation by 2. So we get into, let's see. So we have 2 phosphorus solid plus 3 Cl2 gas goes to make 2 PCl3 liquid. And because I multiplied the equation by 2, I've got to multiply my enthalpy by 2, which comes out to be a negative 613.4 kilojoules. Now, when you look at the next thing in line, you want chlorine. But here's the deal. Chlorine comes from 2 different equations. You had chlorine in the equation we already worked with and chlorine in another equation. When you have the desired substance in more than one equation, when you have the desired substance in more than one equation, temporarily skip that substance. We'll come back to it, but let's skip it for now. Usually, not always, but usually it'll work itself out if you take care of everybody else. So let's move on to the 2 SOCl2s, which I've already dealt with that equation. Because my SOCl2 is only in the first one. I am not going to, so in other words, I can't use anything. I don't need to do anything because the SOCl2 is already taken care of. It was already taken care of in that first equation. Finally, I need to pay attention to my POCl3. So I look for an equation with POCl3, and the only equation with POCl3 is my second equation. I want POCl3 as a product. It is a product. I need 2 POCl3s. I only have 1. So I'm going to multiply this second equation through by 2. So you get two PCl3 liquid plus O2 gas goes to make 2 POCl3 liquid. And because I multiplied that equation by 2, I've got to multiply its enthalpy by 2. So that's an enthalpy of a negative 651.4 kilojoules. Okay, so what I did is I've walked through the target equation, but I still have reactions left over. When you've walked through the target equation and you still have reactions left over, that means that you're going to be using that reaction to get rid of some stuff, probably. When you walk through the target equation, you still have stuff left over. A lot of times that means you got to get rid of some stuff. Looking at what I have so far. My PCl3 liquids have disappeared because I have a PCl3 liquid on the reactant side and I have a PCl3 liquid on the product side. But that's all that's disappeared. And what I noticed from my original reaction is I don't need 2H2O liquid. I don't need O2 gas. From the original reaction, you don't need any of those. So we got to get rid of those. Let's see. And I don't need HCl either. So I got to get rid of all of those things because I don't need them in the original equation. So this last equation is going to be used to get rid of those things. Now, I have 4 HCl on the reactant side, but in the equation I was given, I have 4 HCl on the reactant side. So I'm going to have to flip this if I want to get rid of HCl. And because I did have 4 and there is 4, I'm just simply going to be flipping this. So that equation comes out to be 2 Cl2 gas plus 2 H2O liquid goes to form 4 HCl's gas plus O2 O2 gas. And because I flip it, I change the sign of it to a positive 202.6. Now, if you look at this, the H2O liquid is going to cancel with the H2O liquid in that last equation. The HCl is going to cancel with the HCl in the last equation, and the O2 is going to cancel with the O2 in the last equation. And when you add these 4 equations together, you now get 2 SO2 gas plus 2 P solid plus, now there's 5, 3 here and 3 in the second equation and 2 in the last equation. So plus 5 Cl2 gas goes to make 2 SO2 Cl2 liquids plus 2 POCl3 gas liquid, excuse me, which is the equation I wanted. They match up. Folks, if you will do that step, you can tell if you made a mistake somewhere. Because if they don't add up to that target equation, you've made a mistake. And since they do, now I am going to add these enthalpies together. And when I do so, I get an enthalpy of a negative 1082.8 kilojoules. Questions? Yes. Well, it's technically so when I say these kilojoules, this actually is a great question. I love that question actually, because what this means is it means that there is a negative 1082.8 kilojoules per 2 moles of SO2. There is negative 1082.8 kilojoules per 2 moles of P, or there is negative 1082.8 kilojoules per 5 moles of Cl2, and I can continue. With Hess's law, you don't need to write the kilojoules per mole. Because it is dependent upon how many moles of substance there are. And usually if you just say per mole, that means per 1 mole. And that doesn't quite fit here. Let me give you one to work on. And see how it goes. Calculate the enthalpy. For 2OF2 gas plus 2 sulfur solids goes to make SO2 gas plus SF4 gas with, given, I should say, OF2 gas plus 2 H2O liquid goes to make O2 gas plus 2 HF gas with an enthalpy of negative 276.6 kilojoules. Then you have SF4 gas plus 2 H2O liquid goes to make 4 HF gas plus SO2 gas with an enthalpy of negative 827.5 kilojoules. And you have sulfur solid plus O2 gas going to make SO2 gas with an enthalpy of negative 296.9 kilojoules. I want to give you a few minutes to try to work through that, and then I will come back and walk it through. And yes, folks, you can bring highlighters on the test if you think it will. I use it because it helps keep track. That's when I was just realizing that myself because I was looking at it. Doesn't make sense. That's the problem. Now it's balanced. Okay, the first equation was not balanced, which I actually caught because I couldn't get rid of everything I needed to get rid of. So I was doing the math with you. And basically, folks, I got it off of somebody else's work and I didn't do the problem ahead of time. So I was trying to work it with you and not just assume, and that way I go slow. Okay, so I gave you the equation 2OF2 plus 2 sulfurs goes to form SO2 gas plus SF4 gas. I gave you 3 equations to work from. The first one was not balanced, so it had to be balanced. Now, what I saw when I was working through this is the first thing I saw was I needed OF2. My first equation had OF2. It's the only equation that has OF2. I noticed that I needed 2 OF2s, but I only had 1. So I multiplied this first equation through by 2. And that's when you got 2 OF2 plus 2 waters goes to form 2 oxygens plus 4 HFs. The next thing I worked on is I worked on the sulfurs. I only had 1 equation with sulfur, and that was the last equation. I noticed that I needed 2 sulfurs, but I only had 1. So I had to multiply this equation through by 2 as well to give 2 sulfur solids plus 2 oxygen gas goes to form 2 sulfur dioxide gas. And because I multiplied the equation by 2, I multiplied the enthalpy by 2. I continued on in my pursuit through this stuff. And the next thing I noticed was sulfur dioxide. But I had 2 equations with sulfur dioxide, so I skipped that temporarily. And went on to the SF4. And when I got to the SF4, that allowed me to use my third equation. I needed 1 SF4 in the products, which I had the SF4 in the reactants. So that meant I had to flip this equation. And when you flip it, you flip the sign. Now, if you've done everything correctly, the HF disappeared. The sulfur dioxides, well, let me get all of it. Let's go. OF2, water liquid, the waters disappear, the oxygens disappear, and one of the, let's see, so I had, let's, where's, did I screw up something? Let me see if this one's balanced. Where are my sulfur dioxides not canceling? Oh, no, they shouldn't cancel. One of the sulfur dioxides cancels out, leaving one left over. And so this reaction becomes 2OF2 gas plus two sulfur solids goes to form SO2 gas plus SF4 gas. And the enthalpy of that reaction is A negative 319.5 kilojoules. What you will notice, folks, is even somebody that's been doing this a while has to go back and forth and look at it. Hess's law is kind of like a puzzle, where you work it back and forth until you get the target equation from the desired reactions. Yes.
So when you, when you temporarily skip, like when do you ever get to it, or do you have to?
Normally, when I can temporarily skip something, that something will flush out if I take care of everybody else. Just like, so basically, by taking care of the OF2, the sulfur, and SF4, this SO2 took care of itself because there was one that canceled out one of these. So you temporarily skip it because it's in multiple equations, but normally it will go ahead and cancel out to the correct information once you're done. There is going to be an occasion where that's not the case, where you have to go back and figure out, okay, how do I use the equation to get what I need? But a lot of times it will flush itself out. You had a question.
You haven't answered it.
Okay. So yeah, it's just I skip it temporarily because it's in more than one equation, hoping that with the hope that the rest of the equation or the rest of the information will kind of flush it out. Only when I get down to the end and I haven't flushed it out, do I go back and actually look at it and try to figure out how to make it work. Questions? Okay. That is Hess's law. The last thing we're going to go over in the energy chapter is going to be determination of enthalpy of reaction under standard conditions from enthalpies of formation under standard conditions. So first of all, that little knot that is the superscript means standard conditions. So the question is, what are standard conditions? For an aqueous solution, that means we're dealing with a 1 molar solution at 25 degrees Celsius. For a gas, that means we're dealing with 1 atmosphere of pressure at 25 degrees Celsius. The aqueous and the gases are the only ones that have clear definitions. And that's because when you start thinking about reactions, solids don't have, they don't change their concentration drastically. Whereas a aqueous solution, you add just a little bit more solid and it's going to change its concentration. Solids don't change their concentration drastically by themselves. Neither do pure liquids. So it's strictly the aqueous and gases that come into play. Now, we can calculate the enthalpy of a reaction from enthalpies of formation using the equation that it is the sum of the products of the number of moles times its delta H of formation under standard conditions minus the sum of the reactants times the number of moles times its delta H of formation. Under standard conditions, where the capital sigma means sum. And again, delta is final minus initial. Products are the final piece of a reaction. Reactants are the initial piece. Yes. You are given the formula, but you're, the more important thing though, because the formula is not that rough relative, is you have to be given the delta H's formation. You're not expected to know those. They are found in tables. So you have to be given the delta H's formation. So let's look at an example. Let's calculate the enthalpy of reaction for sodium hydroxide solid reacting with hydrochloric acid gas to form sodium chloride solid plus H2O gas. Given that H2O liquid has an enthalpy of formation equal to negative 285.8 kilojoules per mole. H2O gas has an enthalpy of formation of a negative 241.8 kilojoules per mole. Sodium hydroxide solid has a delta H formation of a negative 426.8, I'm sorry, 426.7 kilojoules per mole. HCl gas has a value of a negative 92.3 kilojoules per mole. And NaCl solid has a value of a negative 411.0 kilojoules per mole. Now, we know our equation, delta H of the reaction is going to equal the sum over the products of the number of moles times the delta H of formation minus the sum over the reactants times the number of moles, or of the number of moles times delta H of formation. Now, it's products minus reactants. So we're going to start with an NaCl solid. So our delta H of reaction is going to equal 1 mole of NaCl times a negative 411.0. Water in a gas form. That is important. I actually put the both waters up here for a reason, because it's not only the substance, but it's the state of matter that are important. So you have to choose the correct one. I need water gas. So that means it's plus 1 mole of water times negative 241.8 kilojoules per mole minus the reactants, which was sodium hydroxide solid. So one mole of sodium hydroxide times negative 426.7 plus 1 mole of HCl gas times negative 92.3. When you key that into the calculator, you'll get a delta H of reaction equal to a negative 133.8 kilojoules. Questions?
So you're just multiplying number of
Now, if I'd have had 2 moles up here, I would have multiplied it by 2. But because all of my coefficients were a 1 in this particular case, that's why they're all multiplied by 1. So it depends upon what the coefficient is. The other thing I wanted to mention, and I'm going to start with a couple of these problems in lab today, just because this is on the exam. The other thing I wanted to quickly mention is that the delta H of formation for an element in its standard state is equal to 0. That is actually important when we get, because that is how all of these delta H's of formation were determined, as we started with the elements in their standard states. Again, I'm going to pick up with a couple more of these examples to start lab, just simply because they are on the test on Tuesday, but then we will deal with gas laws in lab today. No, everything we've covered through what I just finished is on the test Tuesday. The only thing that will not be on the test Tuesday is the gas law piece. I will see you in lab, and it's in 103. Again, it's in 103 today.